Now that we added to um, our library of functions many new functions, we are able to form several functions, more complex functions, and we would be interested to study them. So we need to know their behavior, local behavior at particular points, or infinite behaviors. So as we studied in the chapter of limits, we saw that there were situations that we called indeterminate forms, that where we couldn't give an answer about our computations. We needed to work more on our formula so that we can conclude. So it is important to know how to overcome those difficulties. So let's remind what are the indeterminate forms. So indeterminate forms that are falls in the categories. So infinite, like behavior infinite over infinite, a behavior like 0 over 0, a behavior like infinite minus infinite. Another behavior is infinity times 0. What else? 1 power infinity. What else? Then infinity power 0 and 0 power 0. Okay, so we have those those behaviors that we categorize it as indeterminate forms because we cannot conclude. So there is L'Hopital's rules allow us to overcome these difficulties and find the answers. In particular, for the first two indeterminate forms. Okay, so what does it say? So for the situation indeterminate form, so let's write what the theorem says. So for the indeterminate form, 0 over 0. Okay, so if we have to compute, we are in this situation. So maybe I should just write it like that. We are in this situation. So see, if we are in situation if we have fx approaches 0, okay, and a function g of x approaches 0, as x approaches either a number to the right, or x approaches c to the left, or x approaches just c, finite number c, or x approaches infinity, or x approaches minus infinity. So all those cases can be included. So if we are under those assumptions, then limit, or just let's write directly what we want to say. If we have limit of the derivative f prime x over g prime x as x approaches so I don't want to repeat, so let's erase this. So if you have the ratio approaching a number L, then okay, then fx, you can deduce that fx has the same limit. Then fx over g of x has the same limit. Okay, and similarly, if we have for the indeterminate, the second situation of L'Hopital's rule is the following. So you have indeterminate form infinite over infinity. If we are in this situation, that is, you have fx approaching infinity and g of x approaching infinity as you have x approaching c plus as previously, x approaching c minus, x approaching c, x approaching plus infinity, or x approaching minus infinity. Then if your ratio f prime x over g prime of x approaches L, then we can deduce that the ratio of x over g of x approaches L, the same limit. So this is what the L'Hopital's rule says. Okay, so it is valid when you have a ratio. You are interested in computing limit of a ratio like that of two functions, and you know the limit of each of the numerator and denominator approaching either 0 0 or infinity of infinity. And so if you derive the numerator and denominator, you get the limit, finite limit, then this will be the same limit as our function. Okay, so this is what the theorem says in most in its most generality. Okay, there is let's give some remark here. If we have if we have, for example, indeterminate forms, so just some remarks. Okay, so the case of indeterminate form in the type infinite times 0 or infinity minus infinity, the suggestion is to use algebraic operations or manipulations. Okay, it's more algebraic manipulations. I mean, algebraic manipulation. Okay, to bring the form, the indeterminate form 0 over 0 or infinity over infinity. So then we can apply L'Hopital's rule. Okay, the second situation, if we have indeterminate case of indeterminate forms like 1 power infinity or 0 power 0 or infinity 0, then use here, the hint is use limit, take the ln of your function. Okay, so your function, use this argument. Okay, the ln of the absolute value or just the function fx as x approaches, okay, first approaches your c or something like that. Okay, then deduce um, then deduce limit of fx as the limit of the exponential of ln of fx. So this is the idea. Okay, so mainly this is what we want to know. So now the rest, of course, the difficulty is to learn as much as techniques of algebraic manipulations. This is we need to know, to learn many recipes so that we can think about them, manipulate in particular direction our calculations. So it comes with practice. You need to do that. Here also you need also to practice a lot. So let's do then. So let's do some few examples here. Okay, so the first one, here is the first example. Just an application. So limit, what about limit x2 over 1 minus cosine x as x approaches 0. So I check first. So try first substituting, since I have continuous function. If I substitute numerator 0, denominator cosine 0 is 1, 1 minus 1 0. So I have an indeterminate form. So I have an indeterminate form. Let's write it here, or let's say have, just for me, I write this to say that I have this indeterminate form, so I can use, which justifies the use of L'Hopital rules. And for L'Hopital rule, we will use an H here to say I will use Hopital rules. So it will be limit, okay, so it will be equal to the limit of the derivative of numerator, the same if it exists, okay, and derivative denominator, okay, which is 0 minus cosine x minus with minus so sine x, okay. So now let's try to substitute again. So we will have then 0 numerator, 0 denominator. We have an indeterminate form in type with type 0 over 0, so I can use L'Hopital rule. Okay, so why not? So it will be limit of 2 over this time cosine x, which gives me 2 as x approaches 0. Okay, so here is we applied L'Hopital's rules 2 times. Let's look at this example. Let's now look at this one. Limit of, let's change the color first. Yes. So what about limit of x over square root of x2 plus 1 as x approaches plus infinity? So I see that I have a behavior infinity over infinity, so I can use L'Hopital. So it will be limit as x approaches plus infinity of 1 over, here the derivative is 2x over 2 square root of x2 plus 1. Okay, great. Now I need then to rewrite my function, so I will have square root of x2 plus 1 over x as x approaches plus infinity. Again, I see that I have an indeterminate form in the of type, so I will have an indeterminate form infinity over infinity, so I can use L'Hopital again. Okay, so it will get limit as x approaches plus infinity, or just let's write things here. So let's write here. Okay, so I have infinity over infinity as behavior, so I can use L'Hopital. It will be then limit equal to x over 2 square root of x2 plus 1 over 1 as x approaches plus infinity. But then I come back, I have exactly the same limit at the beginning. And if I keep repeating, I will get exactly the same thing. So I am not able to conclude because, yeah, see, it doesn't stop. Okay, so here we need, so the process doesn't stop. Okay, the process is cyclic, cyclic. Okay, we need to find another way. So you see, even L'Hopital's rule sometimes doesn't allow us to conclude. We need to work differently to find another method, another way. Okay, so another way, yes, here the idea is to, yes, another way is to take, choose the highest power. We did this, usually we did it, so I can take x2 here as 1 plus 1 over x2 as x approaches plus infinity, and see that it is, I can take it away, x square root, I'm working at plus infinity, so the square root of x2 is x, it's positive, that's why I didn't put the absolute value. Okay, so then you can simplify and get your limit, you see. Okay, another last example is about using the exponential. Okay, just to have all, yes, the hint they gave us here. Another example, let's give here example. Okay, what about limit of x power x as x approaches 0 plus? So here we have, so let's apply this remark. So we can write as limit a x ln x as x approaches 0 plus. Then I come and focus on this limit, what it is. I need to find it. Okay, so I will look at it. So limit x ln x as x approaches 0 plus. So if you try to substitute, I will get 0 and minus infinity. So in it's non-determinate form. So in this category, so let's manipulate our algebra manipulation to bring ourselves to the limit, the indeterminate form where we can apply L'Hopital's rule. So here the idea is to write things like that. Look what happens. Now I know that the numerator approaches minus infinity. Okay, so I have infinity and denominator 1 over 0 plus infinity. So it's true. So I can use L'Hopital. Okay, so L'Hopital then says it's the same if the limit exists of derivative of numerator and derivative of denominator. Okay, and now look what happens. So let's modify, simplify. So I will get then minus x as x approaches 0 plus, which is 0. Okay, and then come back here. Okay, come back here. So, and say its limit. So sorry. So it will be then the exponential limit of x ln x as x approaches 0 plus, which is a0, which is 1. Okay, so this is how you can proceed, and you see the steps of the main difficulty is practical. You need to know more techniques, more recipes. Okay,